when we are multiplying with another matrix when we're doing the transformation. Right? And so this critical equation is the correlation matrix of Y, covariance matrix of Y is Q times Cx times Q transpose. And that's what every of our further considerations are based on. And so with that, it's relatively straightforward to now compute what we are actually going to get. And because we're saying that our Cx just has the structure of A, B, and then 0, 0 on the off-diagonal elements because we have uncorrelated entries. And then all we need to do is basically multiply that with a matrix Q that has the structure C minus S, S, C. And so when we're plugging that in here, we're getting that our Cy turns out to be a C square plus BS square. Similarly, sorry, a S square plus B C square. And then the diagonal elements are A minus B CS, A minus B CS. So once we have that, it now becomes easy to see, first of all, that if A equals B, we're always getting 0 on the off-diagonal elements, meaning that we have an uncorrelated result. So A equals B, we have then our Cy being a diagonal matrix, A, 0, 0, being A, I, 2. So this actually has some very important practical applications. For example, when you have uncorrelated noise on certain, let's say, antenna elements in a wireless communication system, and you're doing any unitary matrix multiplication, and so the matrix that we have here for the Q is an example of a unitary matrix. Right? But more generally, any unitary matrix multiplication doesn't change the properties of the noise. So if you have uncorrelated noise, sorry, I should be more precise. It doesn't change that if you go with an uncorrelated noise in, you have at the output again uncorrelated noise. So even though the realizations of the noise at these antenna elements, right, the output of the transformation might be different from the realizations at the input, statistically speaking, the output and the input are completely equivalent. Now, the other question was, well, if sigma 1 square, sorry, if sigma 2 square is larger than sigma 1 square, so in other words, if A is not equal to B, then under what circumstances are we getting uncorrelated results? And again, that's easy to see, right, because we're basically requiring that A minus B times CS has to be 0, and now we know A minus B is not equal to 0, so either C is 0 or S is 0, and that means that the angle theta has to be 0, pi over 2, pi, and so on. So basically some n times pi over 2. Okay, that was the answer to this question. Now, as I promised, today is probably going to be one of the most mathematical lectures that we're going to have in this whole course. And so we're going to start out with a brief repeat of probability bounds. And of course, we already talked about Markov and Chebyshev inequality. Today we're going to talk about the Chernoff bound as well. Then we're going to go to the question of convergence. And that can be a very tricky thing because it always seems very intuitive. Oh, some sequence converges to a particular value, right? Everybody thinks that, that we know what that means. But there are actually 4 different definitions of convergence, all of which are different and which are different in applicable cases. So we're going to discuss those because afterwards we're going to get to the central limit theorem. And there, the question of convergence plays a very big role. And in particular, if you take the wrong definition of convergence, you might actually end up with very wrong conclusions. So that's the general outline of the lecture today. So just... And by the way, the probability bounds do play a role in the definition of the convergence, so it's all one builds upon the other. So just that you're not wondering, well, why are we going off on this mathematical tangent right now? It ultimately comes back to the fact that we want to consider this the central limit theorem, and that, of course, is one of the core results in probability theory. So that being said, let's start out with the just repetition of the 2 bounds that we previously discussed. So there is the Markov bound, which said that the probability for x taking on a value larger equal a is upper bounded by the expectation of x divided by a, where we assume that x is non-negative. Then we had the Chebyshev bound, which says that the magnitude of x being larger or equal than a is upper bounded by the expectation of x square divided by a square. And so today we talk about the Chernoff bound. Why is it called the Chernoff bound? Well, because it was invented by Kramer. It's one of the many instances in the literature where something is named after a person who actually didn't come up with it for the first time. Right? Everybody talks about Nyquist-Shannon sampling. That was actually postulated by Nyquist and Shannon about 20 to 30 years ago, 20 to 30 years after a mathematician in England had established it, and so on. And anyway, that's not so important here. The Chernoff bound says that the probability for x being larger or equal a is upper bounded by the minimum over all s larger or equal 0 of e to the power of minus s a times moment generating function of x of s. The minimization is actually for all the s for which mx of s is finite. So before we go into the proof, let's just compare these 3 bounds here. Usually, the Markov bound is somewhat looser than the Chebyshev bound, which is, again, looser than the Chernoff bound. I'm going to show you a little example of what numerical values we are going to encounter later on. So then you might wonder, well, if we have that Chernoff bound, why did we even bother with the other bounds? Well, because each of them is requiring different amounts of knowledge for the evaluation. And for the Markov bound, all I need is the expectation. For the Chebyshev bound, I need the second moment, and for the Chernoff bound, I need the full moment-generating function. You could, of course, say that, well, if I know the moment-generating function, I might just as well invert it, and then I can find out the probability of the CDF exact, or the probability of being larger than A exactly, because that's just the CDF. And the reason why the Chernoff bound is still useful is that, well, in a lot of situations, that inversion is not necessarily easy. And to remember that it might be an inverse Laplace transform, which requires integration over complex plane, the residue theorem, and so it's still useful to have this particular bound here. So let's now prove the whole thing. Well, we're saying that the probability of x larger equal A is the expectation of the indicator function between A and infinity of x, which can be upper bounded by the expectation of e to the power of s, x minus A. Right? And then we can pull out the e to the power of minus sa times the expectation of e to the power of sx, and that is, of course, by definition, the moment-generating function. Now, this here is probably the most critical step, that we're saying that, well, the indicator function is upper bounded by this term here. It is actually very similar to what we already used in the proof of the Markov bound and of the Chebyshev bound, and we're just saying that, well, the indicator function is essentially a step function here, and so this here has the value of 1. And of course, each e to the power of sx minus a goes through that point. Sorry, this is 1. So things are always looking like this. It's exponents, and basically with different curvature, or however you want to call that parameter s here, and that essentially means that, but all of them are going through this point because this is just e to the power of 0. So since you have a whole family of upper bounds here, and that might be looking like this, you're ultimately saying that, well, since it has to hold for any one of them, it means that minimizing over all possible values of s then gives us the best bound that we can think of. Yes?
Why is probability of x greater than a equal to the expectation of the indicator function?
Well, because you're basically because you're basically just saying that what is the expectation? Right? It's the integral over the probability density function multiplied with. So let me give you a numerical example. So we have here x being proportional to b. So it's an exponentially distributed random variable with a parameter lambda equal to 1, and just try to make it as simple as possible. And we are picking now that we want to find out the probability that x is larger or equal than 7. And we want to do that exactly as well as according to the bounds. And of course, in this case, there's really no need to use the bounds because exact probability is so easy to compute. And this is just the integral from 7 to infinity of e to the power of minus x dx, which is e to the power of minus 7, which is 9.1 times 10 to the power of minus 4. I did not do that in my head. I quickly calculated that for this lecture here. Then we can look at the Markov bound. So we're saying expectation of, the probability of x larger equals 0 is, of course, upper bounded by expectation of x divided by 7. And we know that the expectation of x for an exponentially distributed random variable is 1 over lambda, which in our case is just 1, right, divided by 7. And so that is, therefore, 1.43 times 10 to the power of minus 1. And so just comparing these two values is just a reminder again about how loose the Markov bound can be, especially if you have a pretty strongly decaying function that you're bounding. When we're looking at the Chebyshev bound, then we know that the expectation of x squared is 2 over lambda squared, which equals 2. And so therefore the probability of x being larger or equal than 7 is upper bounded by 2 divided by a squared, which is 49, which is now 4.1 times 10 to the power of minus 2. So a little bit better, but still quite a distance away. And finally, when we're looking at the Chernoff bound, we know that the moment-generating function is lambda over lambda minus s. So therefore, e to the power of minus sa times moment-generating function is e to the power of minus 7s divided by 1 minus s. Now we need to minimize that function over all possible values of s larger equals 0. And that's, of course, very straightforward. We take the first derivative, set it to e to the power of minus 7s times 7s minus 6 divided by 1 minus s squared has to be equal to 0. And so the only way we can achieve that is, of course, if s is 6/7. So we now plug that into the e to the power of minus sa times mx of s, and we get (7 times e to the power of minus 6, which is 1.7 times 10 to the power of minus 2. So again, you see a little bit of progress towards the true value, but we're still more than an order of magnitude away from the exact value. And well, that's just life. That is what we're experiencing with this type of bounds. Yes?
Could you take the limit as s tends to infinity as a valid value s as well?
Yes, so theoretically it's possible that the limit is either for s equals 0 or for s going towards infinity. But then if you're actually plugging in the values for that, and then you're basically just going to see that you're going to get a result that is basically not a numerical value, and you're just basically getting actually what would we get here if we let s go towards infinity? Then I think here the limitation that m of x has to have a finite value for the evaluation would be coming in. So that's basically what is prohibiting this. Good question. Okay, so these were some preliminaries about the inequalities and bounds that we're now going to need in the discussion of convergence. So first of all, what do we mean by convergence? So we consider a sequence of random variables and ask whether they converge, and I consciously leave that under question marks right now, under quotation marks right now, to a random variable x. So that's already one thing that is different probably from what you learned in regular math classes about convergence, because there we were just talking about deterministic sequences, and typically the question is, do they converge to a particular constant value, like do they converge to 0 and so on. Here we're talking about sequences of random variables, asking whether they converge towards another random variable. And this is actually one of the reasons why this is such a can of worms when we're doing the analysis. Now, in terms of the definitions of convergence, I mentioned before there are 4 different definitions, and I'll give you a preview before we go into the details. The first one is a convergence in mean of order p. And it basically is telling you whether the expectation of a pth moment difference is becoming 0 as we're going to infinity. Again, details to follow later. And then the next thing that we have is a convergence in probability. And that one basically says, is the probability density function of the random variables, of the xn, of the sequence of random variables, converging towards the probability density function of the random variable x. Again, everything I'm saying right now, so these 2 minutes here, is somewhat sloppy. I'm just trying to give you an intuitive preview. We get to the exact formulations later on. And one thing you will find is that convergence in mean of order p implies the convergence of probability. Right? So this is the stronger convergence condition. On the other hand, you can have something converge in probability without actually converging in mean to the order of p. And then there is an even weaker expression, which is called a convergence in distribution. And it basically says, is our cumulative distribution function converging towards the CDF of x? Now you might be saying, well, what's the difference? The CDF is just the integral of the PDF, so why is this weaker than this one here? Well, because for the convergence in distribution, we ignore any points at which the CDF has jumps. So, and that enables us to say that, for example, that a sequence of random discrete variables converges to a continuous distribution. Because right, in probability, it can never converge. Something that has delta pulses, basically as it's in its PDF, cannot converge to something that is a smooth distribution. But in distribution, we can actually have that convergence. And we will see this later on when we come to the central limit theorem, that you can have, for example, a sum of Bernoulli variables, which are very clearly discrete random variables, and the sum of n such Bernoulli variables, as n goes to infinity, converges to a Gaussian. But this convergence is obviously only in distribution, not in probability, and certainly not in mean of order p. So that's why we have these sort of 3 different distributions. And then, to top it all off, there is a convergence that is called almost surely. And that really messes things up, because, well, almost surely implies a convergence in probability and convergence in distribution, but there is no sort of order between the convergence in mean of order p and the almost surely. You can have something that converges almost surely but doesn't converge in mean of order p, and vice versa. So these are just sort of 2 different starting points for your consideration of convergence. So that was the starting point. Right? And now let's talk to the convergence in mean of order p. And the definition for that is that the limit for n going to infinity of the expectation of xn minus x to the power of p has to be 0 for the p that can be somewhere between 1 and infinity. So particularly if we pick a p equal 1, then we're talking about a mean convergence. And if we pick p equal to 2, then we're talking about a mean square convergence. So nothing like a concrete example. Right? Let's define a sequence of random variables, xn, and they are Gaussian distributed variables with a variance that goes as 1 over n squared. And we're saying, well, show that square root of n times xn converges in mean squared to 0. So that proof is relatively simple because you just have to insert the definitions that you are encountering, that we hear from the problem statement, into the defining equation of convergence in order n. So in other words, we're saying that the limit for n going to infinity of the expectation of, so we said square root of n, right, times xn, and then minus x, but we're saying x, the x that we want to show it converges to is 0, so we subtract minus 0 here. We can drop that, squared. Want to find what is that limit. So of course we can pull out the square root of n squared, so we have n times the limit of n going to infinity of expectation of, oops, sorry, that of course still has to stay in here, xn squared, and we don't need the magnitude since we're talking about a square anyway. And well, we know that the expectation of n squared is 1 over n squared, because the expectation of the square of a Gaussian equals its variance. So this is 1 over n. Sorry, this should of course be limit for n going to infinity, limit for n going to infinity, and that is 0. Quod erat demonstrandum. And you can also see here immediately that something might converge for a particular order p and not for a different order p prime. And actually, if it converges for a particular p, then it will usually converge for a p prime that is smaller than p, but might not converge for a p prime that's larger than p. So let me also write it down. A sequence might converge in mean, but not mean square, or generally up to order, actually let me call it p star to avoid confusion with differentiation, but not p larger p star. Okay, giving you another example, which is actually called the mean square law of large numbers. So we have x1, the sequence x1 to x2 and onwards are uncorrelated with common mean mu and variance sigma square. And we're defining a mean, this is mn, as 1 over n times the sum of 1 to n xi. So this is basically just the sample mean. And we are stating that the sample mean converges to mu in the mean square sense. So you've heard a lot of different versions of the law of large numbers. And we've previously talked about the weak law of large numbers. We're actually going to repeat that today again. There is the strong law of large numbers. Now we're talking here about the mean square law of large numbers. Basically, all of them are just saying that if you take an infinite number of samples, then the sample mean converges to the actual expectation value. But the subtlety usually lies in the fact of how do we define converges to. And in the weak law of large numbers, it's a convergence in probability. In the strong law of large numbers, it's a almost sure convergence. And here we're talking about a convergence in the mean square sense. So if we plug this in now, then we find that mn minus mu is 1 over n times the sum of xi minus mu. And so therefore the expectation of mn minus mu squared is 1 over n squared times the expectation of I equal 1 to n of xi minus mu times j equal 1 to n of xj minus mu. Right? So remember that trick that we use. If we have the sum of something and then squared, we write that as a sum over these terms with index I multiplied with the sum of the same thing with j. And you cannot just write it as the sum over the I of this term here squared, because that would neglect all of the cross terms. Again, I'm sure you've seen this often in math courses already, but just as a reminder of why we need that here. And so this is now equal to 1 over n squared of the double sum over the I and j of the expectation of xi minus mu times xj minus mu. So what we've done here is basically write this product of the sums as a double sum and pull again the expectation. Right? These are all linear operations, so these interchanges are permissible. And now we do know that the expectation of xi times xj is 0 for I unequal j, because we postulated that they are uncorrelated. So that means this whole thing becomes 1 over n squared times the sum of I equal to 1 to n of expectation of xi minus mu squared, which is now, so the expectation of xi minus mu squared is of course sigma squared, and we have n of these terms here, so we're getting n times sigma squared divided by n squared, which is sigma squared over n, which of course goes to 0 as n goes to infinity. And with that, we've established our rule. So far, so simple, and one might say that, okay, is there something that we can learn from this in addition to what we already know from the weak law of large numbers, or strong law of large numbers? Well, this particular case here also allows us relatively easily to ask the question, what happens if we actually have correlations between the random variables? And just again, to give you a little bit of intuition, and to also show you how dangerous pure intuition can be, I'm telling you again an example from wireless communications. And we've talked previously about fading and how you get different realizations of your channel when you have faded, basically interference of small-scale fading of the different multipath components for you. And so now your channel quality is correlated from one location to the next. And there is a correlation function that basically says, well, if you're very close together, you have a high correlation. If you're far away from each other, you have a smaller correlation. So this looks like, just plotting here the rho, the correlation coefficient, and it looks something like this. And now people really love the so-called block fading model, because doing performance evaluations with a model like this is very, very difficult. So what you replace it with is saying that, well, I'm taking a correlation function that is 1 up to this point here, and then 0 beyond that. And you're pretty much saying that, okay, this is my rho equal 0.5 point. And so you're saying that, well, instead of this smeared out thing, I'm saying that, well, if they're very close together, they're completely correlated, and then there is a jump, and then there is something else. Obviously now any performance evaluation becomes much, much easier. So if we're now looking at such a thing and asking, well, what are the rules of convergence? Does, for example, this square law of large numbers still hold? And for the block fading model, the answer is a straightforward yes. And because you're saying that, let's say this here is 10 samples wide. So you can basically just say, okay, I take my curve, and I pretty much say my first 10 samples are all the same thing. So I map this onto a new sequence where I only take every 10th sample, and then all the derivations for the uncorrelated case hold without any change. So far, so straightforward. But then the question is, well, is that really the same thing as saying I have this smeared out contribution which theoretically enables correlation out to infinity? Do I still have that same convergence? That's not straightforward. So let me show you how you compute this exactly. So we assume now that we have the correlation in the form that this expectation becomes the expectation of, I'm first rewriting it as xi plus k. Right? So instead of saying I have I and j that I'm correlating, I'm looking at I and something that's offset by index k. That's just a change in notation there. We haven't done anything critical yet. But now comes the simplifying assumption, which says this is the correlation that depends now only on k. Right? It doesn't depend on I. Later on, when we're talking about stochastic processes, we're going to see that this is actually the definition of White-Sand stationarity. Right? But for now, just deal with the assumption that, yes, this is what we have here. So now when we're looking at this square law of convergence, and n minus mu squared, then we actually find that this is our expression for the overall convergence. For the expectation of the square. And this just follows from what we wrote here. And that can now be rewritten as 1 over n squared times the sum of I equal 1 to n of c of 0 plus 2 over n squared times the sum over the I, sum over the j, smaller I of c of I minus j. And because this is insensitive to whether we have I minus j or j minus I, we're just writing it in this particular form with a factor of 2 in front of it, which can be rewritten as 1 over n times c of 0 plus 2 over n squared, sum of the I equal 2 to n, the sum over k equal 1 to I minus 1 of c of k. So if we now have that the limit of n going to infinity of 1 over n times the sum of k equals 0 to n minus 1 of c of k is 0, then you can see that this whole expression here still goes to 0. Right? So convergence holds no matter of whether we have a correlation that can extend out to infinity, just as long as this particular condition holds. Now, this is actually a little bit stricter, and that I'm telling you just as a side note, right, of what is really necessary. It turns out that the sufficient condition is actually just that the cross correlation goes to 0 as k goes to infinity. But this here is the thing that you can directly tie to the derivation of the mean square of the convergence in mean square. So if you want to be a little bit more exact in describing how this converges, we can basically say that if this condition is fulfilled, then there exists n such that for all I larger than n, 1 over I minus 1, sum of k equal 1 to I minus 1, c of k is smaller than epsilon. Right? And then we can rewrite the double sum as saying that, well, this is I equal 2 to n, sum of k equal 1 to I minus 1, c of k, which is now the double sum of I equal 2 to capital N minus 1, k equal 1 to I minus 1 of c of k. Now, you note that this is a constant that's independent of n, plus a term that runs from n to small n, I minus 1 times 1 over I minus 1, sum k equal 1 to I minus 1, c of k. So this is smaller or equal than a constant, plus, and now we bring in this condition here, and so this is epsilon times the sum of I equal n to n of I minus 1, which is a constant, plus epsilon of n times n minus 1 divided by 2. So 1 over n squared times the double sum is upper bounded by a constant divided by n squared, right, which of course goes to 0 as the n goes to infinity, plus an epsilon that is arbitrary and arbitrarily small, which means it goes to 0. Okay, that was all I wanted to say for the convergence in the mean of order p. We're going to take a break now. We're going to resume at 9:08. It's 9:08, let's resume. So when we're talking about convergence in probability, we're really talking about something strongly related to the Markov inequality, because we're essentially saying that, well, we want to ensure that the limit for n going to infinity of the probability that xn minus x is larger or equal than epsilon is 0 for all epsilon larger than 0. And so epsilon can be arbitrarily small, but we're still saying that it's larger than 0. And that essentially just says that, well, the probability that the random variable xn with a very large n is away from the converging value x by more than epsilon is 0. So that tells us essentially that, how the convergence works. And it's very easy to show that this is already implied by the convergence in the mean of order p, because this expression here, right, is just upper bounded by the expectation of xn minus x divided by epsilon, and that according to Markov inequality. And this one here is exactly the expression that we analyzed in our convergence to the mean. And so if it converges in the mean, it converges in probability. Now, just to show you that the converse is not true, so you can have convergence in probability, without convergence in the mean. So we let xn be n times an indicator function that is between 0 and 1 over n of a uniform distributed variable between 0 and 1. And so for an epsilon larger 0, the event that xn is larger or equal epsilon is equal to the expression that the uniform random variable is smaller or equal 1 over n, if n is larger or equal than epsilon, or it's 0 if n is smaller than epsilon. Right? So now we can show that this converges in probability, because the probability of this thing here, xn larger or equal epsilon, is upper bounded by the probability of u being smaller or equal than 1 over n, which is 1 over n, and which goes to 0. So converges in probability. But if we're looking at convergence in order p, right, so then the expectation of xn to the power of p is n to the power of p times the probability of u being smaller or equal than n, 1 over n, which is n to the power of p minus 1, and this does not converge for any p larger or equal than 1. And then finally, we're looking at the convergence in distribution. And that is defined as the limit for n going to infinity of f, meaning the cumulative distribution function of xn of x, should be fx of x. And that holds for all x element of c of fx. And here comes in what I was already mentioning before, this, and I'm going to write it down point by point. This is the set of points where fx is continuous, whereas the jump points are disregarded. Right? So this is the reason why it works for convergence of a distribution of discrete random variables to a continuous distribution. And so to provide an example, and let xn be exponentially distributed then, with a parameter lambda equal to n. And then we know that f xn of x is 1 minus e to the power of minus nx for x larger or equal 0, whereas it's 0 for x smaller, 0. Now, the immediate thought that one would have here is that, well, this is not a proper cumulative distribution function, right? Because it's a left continuous function. However, a CDF must be right continuous. And so you could say that, well, if it's not a proper CDF, then how can this thing converge to the CDF of fx of x? Well, here is where that exception clause comes in, and we have the x equal to 0 is a jump point, and we have a discontinuity in our fx there, and therefore we disregard what's happening at x equal to 0, and at all other points the convergence is fulfilled. One other useful property is that if xn converges in distribution to x, then for every continuous function c of x, yn equals c of xn converges to y equal c of x. I'm skipping the proof here, but it's pretty intuitive, because essentially you're saying the xn converges to the x, and then when you're taking some function of two things that are identical, then you should again get identical things. So now we get to the almost sure convergence. That is, as I mentioned before, a little bit of an outlier, but we define again our sequence xn, which is any sequence of random variables, and x being any other random variable. And we're defining now a set G defined as all the omega in our sample space capital omega, such that the limit of n going to infinity of xn of omega equals x of omega. So you basically define it as a set of sample points such that the sequence of real numbers xn of omega converges to x of omega. And you can also define the GC, right, the complementary set of G, which is the set of sample points for which the convergence does not occur. And we now say that xn converges almost surely to x if the probability of G complement is 0. We can, by the way, also define a convergence of, or converges surely, which is that G complement is the empty set. Occurs very rarely in practice, right? But the almost sure convergence is a concept that you hear very often. Right? And one of the applications for is in the strong law of large numbers, which basically says that the sample mean, which again we already defined, converges towards mu almost surely. So, as I said, we have three laws of large number. We have the weak law, which is convergence in probability. We have the strong law, which is almost surely, and we have the mean square convergence law that is basically convergence in the mean square is with p equal to 2. Okay, all of this was preparatory work. Now we're coming to the highlight, central limit theorem. There's a saying that this is a law that all mathematicians suspect to be true and all physicists know to be true. But the background of this somewhat flippant saying is that, well, there are certain conditions for the central limit theorem to apply, and you'd better keep in mind under what circumstances it is really true and what the limitations are for it. I mean, it's a beautiful theoretical work, but if you don't understand how it's derived and what the limitations and assumptions are in the derivation, you can actually run into some major problems, including violating the second law of thermodynamics and so on. So let's say we are dealing with a sum of random variables. Then generally speaking, if we just add up random variables unscaled, then they go to infinity. If I take uniform random variable between 0 and 1, I add up infinitely many of them, I'm getting infinity, so it doesn't tell us much. Then secondly, if we scale everything, then we're actually getting that it goes to the mean, which is just our law of large numbers. But if we are considering a very particular scaling, meaning we first define our yn as being 1 over the square root of n times the sum of the I equal 1 to n xi minus mu divided by sigma. And so let's say we call this here our zi. This is 1 over the square root of n. Then we get to the law of large numbers. And then we're getting to a random variable. So our yn is going to converge to a y that has a reasonable probability density function or rather cumulative distribution function. And so I just wanted to have this here as a preamble so that you see the connection of, or the importance of doing the right scaling. So the central limit theorem says that the limit for n going to infinity of fyn of y is the function capital phi of y, which is the Gaussian integral. So just for your, as a reminder for you, phi of y is 1 over the square root of 2 pi integral minus infinity to y e to the power of minus t squared over 2 dt. And this particular form here is known also as the Lindeberg-Levy theorem. And sorry, I actually forgot something very important, namely that the xi are independent, identically distributed with finite mean mu and finite variance sigma square. And so these are very restrictive assumptions. We're saying the xi are IID, I mean that the mean is finite and the variance is finite. This sort of goes almost automatically, and if we have any practical example, but that the xi are IID, right, that is a very strong restriction that falls into the category of the particular form of CLT that is called the Lindeberg-Levy theorem. I'm going to tell you afterwards an alternative form as well that is a little bit more general. But let's stick with this thing here for the moment and just prove it. So we say that, or we claim that with this definition of yn, we converge. So what is the characteristic function of yn? Well, it's the expectation of e to the power of j nu yn is, of course, the same as phi z of nu divided by the square root of n to the power of n. And because we have independent random variables, so therefore characteristic function of the sum has to be equal to the characteristic function of the constituent to the power of n. Now we're saying that, well, any e to the power of xi can be represented by a Maclaurin series, 1 plus xi plus 1 over 2 xi squared plus some residue term of psi. So we are now going to write our phi z of nu divided by the square root of n as the expectation of 1 plus j nu over the square root of n times zi plus 1/2 j nu over square root of n zi square plus some residue term, depending on this thing here. And then we can evaluate the expectation for each of the terms separately, because this is 1 minus 1/2 nu square over n. That is when we're evaluating this expression here, and because we've normalized already, so the variance of z is 1. So this is simply this expression here. And then we have a j nu over square root of n expectation of zi, but the z, because of the normalization, is 0 mean, and so therefore this becomes 0, and we're left with the expectation of the residue. And now I am going to skip that part of the proof and just say that it can be shown to be asymptotically negligible. And that means this is 1 minus nu square over 2 divided by n. So now coming back to our expression for the phi of yn, well, this is just, as we said before, phi z of nu over square root of n to the power of n, which is 1 minus nu square over 2 divided by n to the power of n. And then you recognize that, well, 1 minus a over x to the power of x going to infinity is just our exponential function. So this is e to the power of minus nu square over 2, and as we already know, this is the characteristic function of a Gaussian. So if we now want the CLT with unequal mean and variance, then we define a variable Sn squared, which is the sum of the I equal 1 to n sigma I squared. And then we can find that xi minus mu I divided by Sn converges to a standard Gaussian. So in other words, 1 over Sn of the sum I equal 1 to n xi minus mu I converges in distribution, so this is converges in distribution, just a notation, to a normal distribution 0, 1 for n going to 0. Oh, I should try and put it on the same page. If for some delta, this is not a convergence condition, right? The limit for n going to infinity of 1 over Sn to the power of 2 plus delta times sum of I equal 1 to n, expectation of xi minus mu I 2 plus delta equal 0. So that is a condition you've got to check of whether that's actually fulfilled. And so if you have wild variations in your sigmas, then it's not necessarily guaranteed that you have such a convergence to a Gaussian. So you have to consider this in each and every case. Now, before we're coming to applications of the CLT, let's talk about examples where it doesn't work. And it's not that the theorem is wrong, but that there is a danger of applying the theorem in a case that just violates the assumption. So the first interesting case is the sum of log normal variables. You find two statements about the sum of log normal variables in the literature. The first one is sum of log normal is log normal. The second one is the central limit theorem, which says that, well, of course, the sum of log normal is Gaussian. So they can't both be true at the same time, right? So where does the seeming contradiction come from? Well, the statement of sum of log normal is log normal stems from an investigation of what happens if I add up 2 log normals, or maybe 3 or 4. And there, the statement, well, the sum of log normals is log normal, is actually not exactly true. If you look at the moment-generating function of the log normals and you take a product of them, it's not a moment-generating function of another log normal. Right? There are some deviations in it. And the way that people argue is to basically look at the shape of the PDF, saying that, well, eyeballing this is close enough, and if I match the first moment and the second moment of the distribution to of the sum distribution to the exact values, then I get something that is a pretty decent approximation. Right? And this works great as long as you really have a few log normals. As a matter of fact, it turns out even 10, 20, 50 log normals, if you add them up, the shape still looks reasonably log normal, but it's never exact. Right? Now, the central limit theorem only talks about the situation of what happens if n goes to infinity, right? If the number of terms that I have in my sum goes to infinity. Now, from a lot of examples, be it, I don't know, Bernoulli or uniform random variables and so on, we are spoiled, and we think that, well, with 10 or 20 terms, we have a pretty good approximation of a Gaussian already. So there is this sort of fork law that people have in their mind. 20 random variables added up are always Gaussian. And I very much want to warn against that. And it can be a decent approximation under some circumstances, but it can also be completely wrong. And the case of adding up log normals is just such a case, that you really need a very, very large number of terms in your sum before you see something that is actually Gaussian. And now, the second big warning is the behavior in the tails. So you are looking, when we're dealing with the CLT, again, we're saying we have infinitely many terms in our sum. So therefore, the approximation of fxn converging to fx becomes exact for all values. But if you're thinking about what happens far out in the tails, under what circumstances does, for example, the sum of uniform random variables give you something that's out in the Gaussian tails? Well, it has to happen that you are picking very large values, or the almost largest possible values in that uniform distribution for each one of your xn, and then you're adding them all up. And that is not going to be very likely, but it will occur. And so, therefore, but then you have to think physically, well, what is the largest value that I can actually get if I have a finite number of terms? Well, it can only be n, and the uniform between 0 and 1, then the largest physically possible value that I can get is n. So if you're looking in the tails about the potential values of larger than n, you're obviously going to be completely off, because the Gaussian distribution tells you have this and this value, and your actual experimental value is going to tell you, no, you don't. So that brings you to sometimes also physical problems, because you get, for example, for a Gaussian distribution, that in the tails, right, if your, let's say your I and Q part of a signal is Gaussian distributed, then you know that your energy is, that's in phase and quadrature phase of a complex signal, that the energy of that signal is actually exponentially distributed, and that means you have a finite probability of energy that is larger than any arbitrary threshold that you can set, including, for example, the threshold of the transmit power. So you can get situations where the Gaussian model gives you the possibility for received power being larger than the transmit power, which obviously runs afoul of second law of thermodynamics. And so that does not work. Now, under a lot of circumstances, these extreme cases do not influence your overall results, but there are some circumstances where you might. And in particular, because in a lot of problems, a lot of analysis problems, you actually look at at certain tools and tricks where you go to limiting cases of infinitely many receivers, and you pick the strongest out of them and so on. And now you're suddenly operating, well, the strongest among infinitely many receivers is going to get infinite much power, which is going to give you just results that are being unphysical if you are not very, very careful. And so you really have to practically consider those limitations. On a more general note, the farther out you go into the tails, the more elements you need, or the more terms you need in your sum in order to have a good approximation. And so that rule of, if you sum up 20 uniform random variables, you get something that's more or less Gaussian, that holds when you're looking for the main hump of the Gaussian near 0. And if you're going out into the tails, it doesn't hold. Even if you're not above the value of n, even if you're looking a little bit below, just the accuracy of your approximation is not going to be as good as what you have in the center. So under all these circumstances, you have to very carefully consider, is the CLT applicable? Does it give you meaningful results or not? Just as a last example, there is, when you're looking at amplifier design, there is the so-called peak to average power ratio problem. And you have an average power of the signal that you're running through the amplifier, and you have a certain peak power. If your amplifier is nonlinear, then if you're getting close to the peak power, you're getting significant distortions. So you need some sort of backoff. And so if you're now computing what is my peak to average power ratio, then you really want to know what is physically the peak. Because if you assume that your PAPR is Gaussian distributed, then you're always going to have some signals that are going to be clipped and completely be drawn into distortion, right? Because your tail, your potential power goes out to infinity. If you have a reasonable model for it, then that's going to cut off at some point, right? Because no signal that you're generating on your ADCs, be it music, be it communications, right? It doesn't matter, right? No signal is actually going to have that infinite power. So if you're looking at what is your PAPR, what is the backoff you have to have in your amplifier, again, you need to look at the exact model, not just assume, oh, I'm going to have something Gaussian. Okay, with these words of caution, we end for today. Thursday, I'm going to show a few more examples from in terms of applications of the CLT, where it is actually useful, and then we're going to go to the question of sample mean and confidence intervals.